New thrusters. Are we heading to Mars?
Good afternoon and welcome to NASA's Johnson Space Center in Houston, Texas.
The historic Jet Propulsion Laboratory. In tonight's Look at This.
It's an important and I think exciting mission.
We've been trying for 70 years to make it happen, but the technology humanity used up until now is just not enough. Mars is just too far, and this seems like an impossible mission. To get there, you'd need impossibly massive amounts of fuel. So much fuel that the entire mission becomes economically absurd. But there's a better way, actually, electricity. The only problem was that we couldn't generate enough of it. Now, that changed. Let's dive into it. So for centuries, Mars has haunted human imagination, the red planet. And in the last few decades, this wonder transformed into obsession. It's clear that humanity really wants to get there, but why? I mean, we barely finished exploring Earth, and there is so much unknown out there in space. Some might even say instead of investing all that money in trying to get to Mars, we can just make this world better. But this Mars idea is sort of this survival insurance. And as much as I hate insurance, it has a point there. Because asteroids don't like us. Earth has been hit by extinction level asteroids before. I mean, we all learned in school the story of Chicxulub. That impact at 66 million years ago killed the dinosaurs. If humanity exists on only one planet, we're one catastrophic event from extinction. And unlike the rockets we humans are used to firing at each other all the time,
launch it now!
An asteroid the size of a city is enough to end us all at once. So Mars offers this backup. Not a comfortable one. Mars looks shitty, and you couldn't convince me it's a cool place to hang out, but it is a backup. So if humanity has a second planet, it means our species survives. Take that, Chicxulub.
I want to punch you in the face so bad right now.
And that's not all. Mars has water ice in its polar caps and subsurface. It has iron oxide, silicon, magnesium. Over decades, Mars could become a manufacturing hub. I mean, once you're already there, you process local materials instead of shipping everything from Earth. It's way cheaper hitting the asteroid belt from Mars, for example, because Earth's gravity is a beast to fight. But Mars is only 38% of our gravity. Sold you on it, didn't I? Well, before you go packing your bags, you might want to know that the engineering problem here is what's keeping us from reaching Mars. Obviously, Earth to Mars is 140 to 250 million miles depending on orbital positions. At current spacecraft speeds, that's 6 to 9 months of travel. But the problem isn't just getting to Mars. It's keeping humans alive long enough to survive the journey. Yes, in such a long journey, humans will suffer huge amounts of radiation exposure outside our planet's magnetic field. To be accurate, astronauts receive roughly 0.5 millisieverts every day from cosmic rays and solar radiation. A 9-month journey means like 135 millisieverts total. That's about 45 chest X-rays every single day.
Buffalo soldier!
That's a significant cancer risk. Humans also lose bone and muscle. About 2% of muscle mass goes out of the window every month. 9 months means your gym bro will go back to his thin broccoli haircut version. But if NASA, Elon, or any of these visionaries actually find a way to cut transit time, that would change the whole picture. But this requires power, and lots of it. A Mars mission with today's chemical rockets will need 400 to 500 tons of fuel for a crew of up to 6 people. That's almost 7 separate Saturn launches just for fuel. Modern chemical rockets can do better because of the Tsiolkovsky equation. Rocket's mass grows exponentially with each additional meter per second of velocity you want to achieve. But what if you didn't need all that fuel? What if you could achieve the same velocity with 10th the propellant mass? That changes everything. That's electric propulsion. It works thanks to a simple law of physics. Efficiency is all about exhaust velocity, not thrust. So if you're impatient and just want to learn about NASA's new thrusters, jump to part 6. But for now, let's understand how chemical rockets work. A chemical rocket works by burning fuel and oxidizer together. The combustion creates hot, high-pressured gas. That gas expands through a nozzle and shoots out the back. The reaction force pushes the rocket forward. Again, the problem isn't power because chemical rockets are extraordinarily powerful. The problem is its efficiency. In space, after you've already escaped Earth's gravity, thrust doesn't matter anymore. What matters is how fast you can throw your propellant out the back. That's called exhaust velocity. A chemical rocket's exhaust velocity is roughly 3,000 up to 4,500 meters per second, which is, let's say on average, 8,000 miles per hour. But if you want to accelerate 100 tons of spacecraft to Mars and you can only throw propellant backwards at 4,000 meters per second, you need to throw a lot of propellant. The Tsiolkovsky equation says the fuel mass you need grows exponentially, which means, for example, a 3 kilometer per second velocity change requires 20 times the spacecraft mass in fuel. And a 6 kilometer per second change requires roughly 50 times the spacecraft's mass. So for a 100-ton spacecraft, you need 5,000 tons of fuel. Now you need a rocket to launch that fuel tank, which means more fuel, which means bigger rockets. That's endless headache, and there's no way around this with chemistry. What if you threw propellant at 100,000 meters per second instead of 4,000? Then the efficiency becomes reasonable. So bigger explosions out, high exhaust velocity in. That's the idea behind NASA's latest thruster, the electric propulsion. The concept of electric propulsion dates back to 1912. Robert Goddard, the rocket pioneer, wrote about using electrical acceleration to throw propellant backward, but it was pure theory, no way to generate the required power. By 1960s, NASA researchers had concrete designs for electric thrusters. So it goes like this: accelerate ions using electric and magnetic fields, eject them at high velocity, get thrust. Simple. But it required power, steady, continuous electrical power. But solar panels in the 1960s produced maybe 50 watts. An ion thruster needs kilowatts, not even close. So the idea stayed in the realm of science fiction. You see, electric propulsion was never the impossible part. Generating enough power for it was. But in 1998, NASA launched Deep Space One with an experimental ion thruster. Most of the aerospace industry didn't expect it to work reliably. And like all great stories, it proved to work perfectly. The thruster ran continuously for months. Over the mission, it accelerated the spacecraft to speeds it could never have reached with the tiny fuel load it carried. By the 2010s, most commercial communication satellites used ion thrusters to extend their operational life. That's the satellite picture we used to see all the time. And NASA's Dawn mission used ion propulsion to visit multiple asteroids. Now comes into our story Psyche. Psyche is NASA's current flagship example of electric propulsion. It's traveling to an asteroid called 16 Psyche, which orbits in the asteroid belt between Mars and Jupiter, a journey of 2.5 billion kilometers. Now that's what you call efficient. The whole multi-year mission runs on just 3,500 pounds of xenon. That's it. A chemical rocket would need over 50,000 pounds of fuel to do the exact same thing. That's not even a fair fight. And these ion thrusters blast xenon atoms at staggering 81,000 miles per hour. The mission is super efficient, but it's trade-off is that this mission takes years, meaning Psyche's journey takes longer than a chemical rocket would, but with tenth the fuel. For robotic missions, that's acceptable. For human missions, it's not. But the part that's being overlooked is that this mission used relatively low power electric propulsion systems. Psyche's ion thrusters are around 8 kilowatts because generating more power in space is just hard. Solar panels degrade in radiation and efficiency drops with distance from the sun. At Mars distance, solar panels produce maybe 43% of what they would produce at Earth. So if you want truly high power electrical propulsion, megawatt scale systems needed for human Mars missions, you need a nuclear reactor. And nuclear reactors in space are politically complicated. Act surprised. Technically challenging and requires years of development. So at this stage, to conclude this point, scientists know how to build the electrical thrusters and they proved that they work, but they are still relatively weak and slow.
Good afternoon.
That's beginning to change because NASA and other agencies are now developing compact nuclear systems designed to power far more powerful electric thrusters, potentially reaching those megawatt levels. Now back to Psyche. It uses xenon because xenon is stable and available, but there's a different element that works even better at high power, and that's lithium. Lithium, like the lithium battery. This is where the next generation comes in. Let's try to understand how lithium electric thrusters work. We have four main parts here. You have the propellant source, which is just the heated lithium metal vapor. Then we have the ionization region. Here, electricity strips electrons away from lithium atoms, turning them into charged particles, plasma. The third part is the electromagnetic accelerator. Using powerful electric and magnetic fields, the engine violently accelerates those ions out the back of the spacecraft at enormous speeds. And finally, we have the neutralizer. Without it, the spacecraft would just slowly build up electrical charge and then starts pulling its own ions back towards itself like a magnet. Xenon works fine for what Psyche is doing right now, which is just chilling in space. But for a Mars mission, that's not enough. And this is why NASA, for their new thrusters, chose lithium. And you may ask again, why lithium? Because at these extreme power levels, xenon starts reaching its limits. So lithium is much lighter, much easier to ionize, and behaves better inside high energy plasma engines. That means more of the reactor's electricity can go directly into accelerating the propellant instead of being wasted just creating the plasma itself. And because lithium atoms are so light, the engine can throw them out the back at far higher speeds than xenon. And that's the entire game in space propulsion. The faster your exhaust velocity, the less propellant you need to carry. And that's what makes these engines so interesting. A lithium plasma thruster could potentially reach exhaust velocities that chemical rockets simply cannot approach, while using only a fraction of the propellant.
SkyCal's Desmond Shaw is over the historic Jet Propulsion Laboratory in tonight's Look at This.
Well, take a look at this high-tech campus in La Cañada, Flint Ridge. This is the Jet Propulsion Laboratory, or JPL, and it's a federally funded research.
So for the past 2.5 years, engineers at NASA's Jet Propulsion Laboratory had been quietly building a new kind of lithium plasma engine. They first ran it in computer simulations thousands of times, maybe. And now it's time to fire it up and see what actually happens. That day was February 24, 2026, just recently. The condensable metal propellant Comet vacuum facility at JPL is a 26-meter long chamber. It exists mostly for this one reason, which is testing thrusters like this one. The lithium at extreme power is dangerous, as you may imagine. The temperature reaches thousands of degrees. The electromagnetic fields are violent. Lithium vapor can't touch air. It reacts with oxygen and nitrogen and then destroys itself. You need a perfect vacuum. You need water cooling. You need to know exactly what's happening inside and what's about to happen. This is why you have this chamber. So the goal was 120 kilowatts. Just to remind you that Psyche's electric thrusters operate at approximately 8 kilowatts. Here we're talking about 120. No American facility has ever demonstrated a plasma thruster anywhere near this level of power before. Okay, so back to the story. Lithium vapor was fed into an inferno of 5,000 degrees Fahrenheit. The atoms couldn't survive that environment and the lithium becomes plasma. Then a stream of ionized lithium blasted out of the engine at over 100,000 miles per hour, a spectacle physics made visible. All 5 ignition tests succeeded. The system did actually reach the full 120 kilowatts as planned. And according to the engineers, the thruster itself wasn't even close to its limits. So now the real question is no longer whether the engine could survive this kind of power, but whether humanity could build power systems large enough to fully unleash it. What a crazy invention. So what's next, you may ask? The 120 kilowatt test appears to be just a warm-up. Researchers are already aiming to boost each single thruster to somewhere between 500 kilowatts to 1 megawatt in the next few years. So you need to understand there's more than one thruster. So just one thruster needs to be between 500 kilowatts to 1 megawatt. To actually send a crewed mission to Mars, NASA estimates you'll need a total output of 2 to 4 megawatts. So it means like maybe 4 different thrusters that work at the highest power that is available today. So that's going to require a whole cluster of lithium engines working in perfect sync. But the biggest hurdle left is endurance. These engines would need to run non-stop for over 23,000 hours during the trip to Mars. So the plan is to pair these thrusters with a space-based nuclear power source, giving them all the energy they need without relying on sunlight in the deep reaches of space. And as director Isaacman put it, this is a strategic investment that will enable humanity's next giant leap to another planet.